Hey guys, it's Jamie here. So I'm going to do a quick video today about the stream function for low-speed aerodynamics. Now online so far I've just seen YouTube videos which just state the equations, show an example or two, but they don't really give a good analogy of what the stream function actually is. We just end up using it for the sake of it, because we have to use it. So I'm going to give a go at explaining it. Hopefully if you like it, you'll like and subscribe. If you don't like it, still like and subscribe. So the stream function is the amount of flow which crosses a streamline. Well, no flow can cross a streamline, but the amount of flow that crosses a line. And in units, you'll know this as the volume flow rate. It's the same as meters cubed per second. Now I'm going to use an example which is going to be similar to the one in this book, which is Aerodynamics for Engineering Students. It's the 4th edition and it is by E.L. Houghton and P.W. Carpenter. It's a fantastic book. I really recommend it. It'll be really useful for this module and for high-speed aerodynamics. And if you want to go on to this and go further with this in your career, it's a great starting point.
Okay. So, say we have an Olympic-sized swimming pool, which is going to be 25 meters in width and 50 meters in length. Meters in length, 25 meters in width. And say that the depth of the pool is consistently 1 meter. And also imagine that the water is going from left to right at a velocity of 2 meters per second. Now say you're a swimming instructor and you want to split the pool in half so you can have the beginners on one side and the advanced swimmers on the other side. What do? You and a mate, you grab a rope and you split the pool in half using the rope, and you'll see that it curves like so, because obviously the water is going to be moving from left to right. Now the volume flow rate, or more importantly the stream function, will be a product of the width, 25 meters, the depth of 1 meter, and the velocity of 2 meters per second, which will give 50 meters cubed per second.
Okay, so that's just a little physical representation of what the stream function actually is. So let's move on to the velocity components and see if we can further understand what we've just learnt, or further enhance.
Okay, so same example this time. Well, similar example. A pool of 50 meters in length, 25 meters in width, and a depth 1 meter. That was poor M. Velocity of water is 2 meters per second. Now this time, say we put the rope at an angle. This is purely for derivation purposes. And so we have an x and y velocity component. So say we have this rope, like that, and then we have another rope further down in the same shape, like so. Now the stream function for our first rope is going to just be phi. But the stream function for our second rope is going to be phi plus change in phi. So to find the difference between these two ropes, it will be our change in phi. Okay, so we can then use the change in phi to find the velocity components at a chosen point. If you want to understand how the equations are derived, feel free to check out the book I recommended, but right now I'm just going to give you the equations. So the velocity u, which is the velocity acting in the x direction, will be equal to the partial derivative of phi with respect to y, and then the velocity v which is the velocity in the y direction, will be equal to the partial derivative of phi with respect to x, and this will be negative. Again, the reason why it's negative is explained in the book, but it's not necessarily something that you definitely need to understand. You just need to know that it's negative, and it's because of the way it's derived.
That's all we have for you guys today. Thanks for watching. Don't forget to like and subscribe. If you have any questions or corrections that we should make, leave a comment in the description below, and I'll see you next time. See ya. Bye.